Okay, this is the terrific graph that we created. We have two boundary lines for our space constraint and our cost constraint, and this was from 5.1 Pet Sitters. And we're going to use this graph today for the activity for 5.2. So let's make sure we all have a copy of this graph. And 5.2, too big or not too big? That is the question. A solidifying understanding task. Oh, too big or not too big? That is the question. I get it now. As Carlos is considering the amount of money available for purchasing cat pens and dog runs, see below. So, amount of money, let's see. We had a space constraint, all right? And we had a startup cost constraint in 5.1. He realizes that his father's suggestion of boarding the same number of each, perhaps 12 cats and 12 dogs, is too big. Why? All right, let's take a look at this. So, and remember, we graphed these constraints in 5.1, and you have another copy for today's activity, so that's the graph we were just looking at. And here it is right here. So let's look carefully. Why can't we board 12 dogs and 12 cats? And remember, X would be our number of dogs and Y would be our number of cats. So let's plot the point 12, 12 and see where it lies in the first quadrant of the coordinate plane here. So X equals 12, that'd be 10, 11, 12. And Y equals 12. What are my Y's going up by? It looks like 3. 3, 6, 9, 12. That point would be right there. Now, think about the constraints that we dealt with in 5.1. All right. Now, all of the ordered pairs representing X, the number of dogs, and Y, the number of cats that we could board, would have to fall within what we call is a feasible region. And that's the region on or below both of these boundary lines. All right, by the way, let's label that point 12, 12. So X equals 12, 12 dogs and 12 cats. And then there's my feasible region right there. So we can choose any point that has whole number coordinates in this feasible region right here. All right, but look at that, 12 dogs and 12 cats. It is below this constraint, but it's not below our other constraint right here. So that point's not going to work. Okay, so now, number one, find at least 5 more combinations of cats and dogs that would be too big based on the startup cost constraint. Okay, first, too big. All right. I want to make sure I know which boundary line is represented by the startup cost. So I'm going to take this and let's just check the intercepts here. So what's the y-intercept? Let's let x equals 0, and that would mean 32y is 1280. So I'm going to go 1280 divided by 32, and I'm getting a 40 for my y-intercept right there. Okay, and that's the 040 right there. And that means this is the boundary line right here for my startup constraint. And that point looks like 16, 0, but let's double check that. So if y equals 0, 80 times x would have to be 1280. And 1280 divided by 80 is 16. So that's it right there. So find at least 5 more combinations of cats and dogs that would be too big based on this startup cost constraint. So I have to be above this tan line right here. All right. Well, I already have 1 point right there. I can pick any 5 points I want. Now look at how I do this to make it as easy as possible for myself. That's above it. And now I'm going to keep using the same x values and just go up 1 hash mark on the y-axis right here. And that's 1, 2, 3, 4. There's my 5th one right there. So plot each of these combinations as points on the coordinate grid. There they are in red right there, using the same color for each point. So let's label those then. Okay, well notice my x-coordinate for each of those red points is red. And now let's just list our y-coordinates. The y-coordinate of this first point is 15, and we're going up by 3, so that would be 18, 21, 24, and 27. And there's number 1. Okay, number 2. Find at least 5 combinations of cats and dogs that would not be too big based on the startup cost constraint. So the startup cost constraint, remember the boundary line is our tan line right there. So now not too big means we need to be on or below. So let's just check 5 simple points on or below that line. Okay, that would work. And now to keep things simple, let's use the same x-coordinate again. 3, 4, and 5. There they are. Now let's write the 5 ordered pairs representing those 5 points where the startup cost is not too big. So the x-coordinate for each of those points would be 5. And now let's list our y-coordinates. Well, the first y-coordinate is right there, and that would be a 12, and then a 15, 18, 21, and 24. There we go. Plot each of these combinations as points on a coordinate grid using a different color for the points that then you used in number 1. That should have been a that you used in number 1. That's okay though. All right, so we're going to number 2. Number 3. Find at least 5 combinations of cats and dogs that would be just right based on the startup cost constraint. Just right means they would exist on our boundary line. All right, and remember our inequality for the startup cost constraint right here, 80x plus 32y is less than or equal to 1280. Let's do a little practice. You don't have to do this here to answer the question, but let's take this inequality and solve for y, putting it in slope-intercept form, because I have a feeling we're going to need that later anyway. So if I'm going to solve for this y right here, I'm going to subtract the 80x's from both sides. There we go. And adding or subtracting does not affect our inequality. Less than or equal to 80x minus 80x cancels, leaving my 32y's would be less than or equal to negative 80x plus 1280. Now let's divide every term by 32 to undo this multiplication by 32. Less than or equal to, notice I divided by a positive. It does not affect my inequality symbol. And 32 divided by 32, those would cancel, leaving my factor of y. And now let's see how we can clean up this. Look at this. A negative over a positive will be negative. And then I think we can reduce this fraction 80 over 32. What's the biggest number that goes into 80 and 32? Doesn't 16 go into 80 5 times? And 16 goes into 32 2 times? That negative 5 over 2 looks way prettier than negative 80 over 32. And don't forget your factor of x right there. And then I'm hoping 32 goes into 1280 evenly. Let's check this out. 1280 divided by 32. Please punch this out on the calculator with me. Oh yeah, and look at that. I'm getting 40, which I expected because look at the y-intercept at that boundary line, 0, 40. Very good. And this is y is mx plus b. My slope is negative 5 over 2. And my y-intercept is 40. Beautiful. Now, the reason I did this, though, is I want you to really see what this constraint means right here. You know, in this form, I have a pretty good idea. This is general form of this inequality. But in slope-intercept form, I can clearly see y is less than or equal to. The cost exactly is the equals, and that's the stuff on the boundary line that has a y-intercept of 40 and a slope of dropping 5 and running 2 right there. Okay, so let's see, I missed something there. What did I push? Okay, anyway, so I think I'm going to do points on that. Yes, I am. There it is. Okay, so how many points do they want that are perfect, that are on the boundary line? Remember, plot each of these combinations as points on a coordinate grid using a third color. Well, I'm going to use the one I know already, 0, 40, right there. Now, you know, I could use the slope and drop 5 and run 2, drop 5 and run 2, but I'd like to kind of span this entire boundary line a little better. So I think I'm going to take the slope and I'm going to look for, what if I drop 10 and I run 4? Dropping 10, 40 would go down to 30, and then 1, 2, 3. See, that's perfect right there on my grid right there. I dropped 10 and I ran 4, and there I am right there. See? So what's the coordinates of this point? Now, the reason I'm doing this again too is, let's go ahead and write down this slope. M equals, rise is -10, run is 4. That's the same slope as -5/2. It's just not reduced all the way. All right. But now watch what I can do here. Look at the x-coordinate. How far am I running to the right? 4. So I go from 0 to 4. And look at the y-coordinate. How far am I dropping? 10. So 40 would go to 30. And that pattern's just going to continue. Watch this. Let me put another slope triangle in here. And then that point right there. What's the coordinates of this point right here? Well, the pattern continues. X goes from 0 to 4 to 8. Y goes from 40 to 30 to 20. And then let's do it again. Another slope triangle. X is 0, 4, 8, 12. And Y is 40, 30, 20, 10. And this is working out perfect because watch. One more slope triangle to get to this point right here, which is my y-intercept of that boundary line. All right. And what is that, by the way? Wouldn't that be 16, 0? Well, watch this. 0, 4, 8, 12, 16. And then 40, 30, 20, 10, 0. It worked perfectly. All right, so there we go. Now let's make sure we've answered the questions. Okay, find at least 5 combinations of cats and dogs that would be just right based on this startup cost constraint. That is, find the combinations of cat pens and dog runs that would cost exactly $1,280. Plot each of these combinations as points on a coordinate grid using a third color. So each of these points in black right there represent the ordered pairs right here, and I have 5 of them. And if we did 0, let me see what's what again. 0 dogs and 40 cats would cost $1,280. Or I could have done 8 dogs and 20 cats, $1,280, and so on. That's going to be our startup cost constraint. Very cool. Okay, what do you notice about these 3 different collections of points? Okay, remember, my red ordered pairs, too big. My blue ordered pairs are fine, and they're below, so they're below the cost. And then my black ordered pairs are just right. So let's see how we write. Too big, red. Okay, and those points are all above the boundary line. Not too big, in blue. And those points are all below the boundary line. And just right, black. And those black points are on the boundary line. Very cool. Okay. Write an equation for the line that passes through the points representing combinations of cat pens and dog runs that cost exactly $1,280. What does the slope of this line represent? Okay, well, we've already done that as an inequality, and there it is right here. But they asked for the equation for the boundary line. So see that less than or equal to? We just need an equation. I need y equals. That's going to represent this tan boundary line right there. So y equals -5/2x plus 40. And notice how I put the slope in red and the y-intercept in red? So we can go a little farther. What does the slope of this line represent? Well, I am rising -5 and I'm running 2. All right. Now, the rise, that's y, those are cats, the x's are dogs, right? So x dogs, y cats, and this implies the slope, if I have 5 less cats, I can have 2 more dogs. So m equals -5/2. 5 less cats gives us room for 2 more dogs. Carlos and Clarita don't have to spend all of their money on cat pens and dog runs unless it will help them maximize their profit. Shade all of the points on your coordinate grid that satisfy the startup cost constraint. Okay, well, remember we did the feasible region for both constraints earlier? But now we're talking about just the one startup cost constraint. Okay? Shade the points. So, and remember, here it is right here. In general form, 80x plus 32y is less than or equal to 1,280. Or in slope-intercept, y is less than or equal to -5/2x plus 40. So that would be every point with whole number coordinates on our boundary line, that tan line, or below it. They're on it or below it. And that is it. Shade all of the points on your coordinate grid that satisfy the startup cost constraint. There they are right there. Beautiful. Write a mathematical rule to represent the points shaded in number 6. We have already done that. That is, write an inequality whose solution set is the collection of points that satisfy the startup cost constraint. And that's the one we did right off the bat. Here it is right here. And again, it could be in general form. 80x plus 32y is less than or equal to 1,280. That would work. I prefer it in slope-intercept, so I can clearly see my slope, my rise and run, and my y-intercept, but both will work. All right, number 8. In addition to startup costs, Carlos needs to consider how much space he has available based on the following. The space constraint, which we dealt with in 5.1. Cat pens will require 6 square feet of space, and cats are y, so that's a 6y, while dog runs require 24 square feet. And dogs are x, so that's be plus 24 x's. And I put the x and the y, x first. All right? Now, Carlos and Clarita have up to, that means up to, I can get there but no more, so I'm going to say less than or equal to, and start working on up to, translate that to algebra. Less than or equal to what number? 360 square feet. So 24x plus 6y is less than or equal to 360. And there it is. Okay. Now, write an inequality to represent the solution set for the space constraint, and shade the solution set for this inequality on a different coordinate grid. Okay, and I put it on the same coordinate grid. I'm going to keep using the graph we have right here. But now take a look. All right, this is appropriate. This is in general form. Or again, we could solve for the y. And if we're going to do that, let's subtract the 24x from both sides. Will not affect our inequality, less than or equal to. And 24x minus 24x is gone, and you have the 6y's. And let's put this with our like mx plus b. So let's go negative 24x plus the 360 because we cannot combine those. Now, let's divide every term by 6. All right, so on the left, the factors of 6 would cancel, leaving the factor of y. Y is less than or equal to, and a negative over a positive is negative. And now, can we reduce 24 over 6? How many times does 6 go into 24? 4 times. 4 times what? That x right there. So y is less than or equal to negative 4x. And now, what is 360 divided by 6? Well, wouldn't that be 60 plus 60? All right, and either general 24x plus 6y is less than or equal to 360, or slope-intercept, y is less than or equal to negative 4x plus 60. Those are both appropriate. All right, but we need to practice converting from one to the other. All right, so let's see. We wrote the inequality. Now shade the solution set for this inequality on a different coordinate grid. So that is going to be, and look at here, in this I can clearly see my boundary line. Do you guys see the y-intercept of 60 up here and a slope of negative 4? Well, negative 3, negative 4, and 1 over about right there. Perfect. So that's everything on or below that boundary line. On or below. There it is right there, number 8. Oh my, that was the end of the lesson? I thought we'd go a lot farther today. We'll probably get there in 5.3. All right, you guys, carefully do your ready, set, go. Get really good at these inequalities and graphing inequalities and solutions that will work or won't work in the feasible region. And get the ready, set, go done and have a great day.